Okay, so last time we talked about the Ferris wheel problem, and what we're going to be doing today is we're going to be looking at graphing that exact same problem. So we're starting with the information here. It says in the previous task Sine language, you calculated the height of a rider on a Ferris wheel at different times t, where t represented the elapsed time after the rider passed the position farthest to the right of the Ferris wheel. So the important facts that we got to remember here, we need to remember that the Ferris wheel had a radius of 25 feet. Okay. The center of the Ferris wheel was 30 feet above the ground, and the wheel makes one complete revolution counterclockwise. Counterclockwise is important, every 20 seconds. Okay. So what we're going to need to look at first here is just thinking about the Ferris wheel. Sketch a quick Ferris wheel here. And we're saying, okay, the radius is 25 feet. So that's going to be the radius right there. Okay, that means the diameter is going to be 50 feet. Okay, and then it says the center of the Ferris wheel is 30 feet above the ground. So we'll just draw a little height here. We're saying that's 30 feet. And then this is going to be the ground down here. Okay. And then the last part, it says the wheel makes one complete revolution counterclockwise every 20 seconds. But the most important part about that is it's saying, hey, we're going to start right here at the farthest right position. And then we're going to go all the way around one full circle, 360 degrees, counterclockwise every 20 seconds. Okay, so that's the information that we need to know about this particular problem. Now, based on that, the data you calculated, as well as any additional insights you might have riding on Ferris wheels, sketch a graph of the height of the rider on the Ferris wheel as a function of time. So what we're going to do here is we're going to say, okay, this axis down here is our time, and the y-axis is representing our height. Okay, so right now we can see that the axis goes from 0 feet all the way up to 60 feet. That's the height, and the time's going from 0 seconds to 50 seconds. So right now I know the center of the wheel is starting at 30 at 0 seconds. Oops, so we're gonna do that. And then every 20 seconds, it's going to be back at 30 again. So it'll be at 30 at 20, and it's going to be at 30 at 40. Okay? And now we have to ask ourselves, if it makes a full revolution in 20 seconds, it's also going to be at 30 feet halfway around the circle. So when I get to the halfway point right here, there's my halfway point. Half of 20 is 10 seconds, so I know it's also going to be at 30, at 10 seconds, and at 30 seconds. Okay? Well, it's going to be at its maximum height halfway between 0 and 10. So that's going to be 5 seconds up here. It's going to be at its minimum height halfway between 10 and 20. So that's going to be 15 seconds. So now I know the center is 30 feet above the ground. It's another 25-foot radius. So the maximum height at 5 seconds is going to be 30 plus 25. So that's going to be 55. So at 5 seconds, we're going to be at the maximum at 55. At 15 seconds, we know we're 30 feet above the ground with a radius of 25, so we're actually only 5 feet above the ground at 15 seconds. So that's the minimum. And then we're going to be at our center point, to our maximum, to our center point, to our minimum, back to our center point. So what that's going to do is that's going to create kind of a wave-looking shape. All right, and this is where our sine function comes from, which Mr. Ford and I spoke about this in our classes already. So our sine function is going to look something like this. At 25 seconds, it looks like it'll be back at its maximum. it's done one full cycle, or what we've also called that is one period of the function. At 35 seconds, it's back to its minimum. At 45 seconds, it's back to its maximum. At 50 seconds, it's back to its center line. Okay? And then I'm just going to draw arrows on my graph to show, hey, this thing keeps going on forever in both directions. But it's going to have some general look like that. Okay, that's what's going on with this Ferris wheel. Now, some important vocabulary we need to discuss here, okay, is what we're going to talk about next on problem number 2. It says, write the equation of the graph you sketched in problem 1. So the first things we need to talk about are the amplitude, okay. We also need to talk about the period of the function. And the last thing we need to talk about is what's called the midline. Right? So the midline, that's going to be what's called the exact center of the graph. In this case, we're going to see the midline right here. I'll do it as a dashed line. Goes right through the very middle, which is all of these values of 30. So the midline here, we'll say d equals 30. We'll talk about why we're using the value d here in a second. Okay, that's just the variable that represents the midline. So I'm going to write that down here as well. When we're talking about the period of the function, a good way to tell where the period is usually from like peak to peak, right there. So that's one period right there. All right. Another way you can tell where a period of a function is from trough to trough. So right here is another example of one period. All right. Or the last way you can tell where a period of a function is, it's a little harder, a little more difficult to tell, is usually from when the function goes up and then when it's going up again through that same midline. So that would be another example of one period of the function. Personally, I like to go from peak to peak or trough to trough. It's a little easier to tell. And in this case, the period of the function happens to be 20 seconds. Okay. The last part, the amplitude, is how high we're going from the midline to the maximum. So the amplitude here happens to be the radius, 25. How high we're going from the minimum to the maximum. And we'll just say A equals 25 for our amplitude. Now the reason I chose these variables is because we're going to have our function written as y equals A times sine of b times x plus d. Okay. A stands for our amplitude. So in this case, A equals 25 sine of bx plus 30. Now the weird part here is the period. Right now the period we have is 20, but the b value is not a period. What we need to think back to first is the parent function, y equals sine of x. We call that the parent function because it doesn't have any transformations happening to it yet. The a value in front is just 1, that's the amplitude. Notice that there's no plus d, that's because the midline is 0. So the parent function is highlighted at that 0 value. Right? So this is where our parent function comes from. The b value in the parent function happens to be 1 as well. In a typical parent function, a full circle is going to be 360 degrees. So the period of this function is 360 degrees. Now, Mr. Ford and I, we talked about these graphs previously in radians. What we're going to be doing today is we're going to be talking about them in degrees instead. So full circle is 360. Okay. If we were looking for the b value, we can find that by saying the period is 360 degrees over our b value. And in the parent function, the b value is 1, so that's why the period is 360 degrees. In this case, the period is 20, so to find the b value, we're going to say 20 equals 360 divided by b. And we have to use our algebra skills to go ahead and calculate what the b value is going to be. So we can multiply both sides by b, so we're going to end up getting b times 20 equals, the b's will divide out on this side, 360. And now we can divide both sides by 20 to find our b value. And in this case, 360 divided by 20 equals 18. So that's how we end up with our b value of 18 for this problem. And that's how we'd write this equation. Our amplitude is 25. That's the a value. Our period was 20, so the b value came out to 18. That's how it was related to the period. And then the midline was 30. So that's where we got the 30 from the midline from. Okay. Now, for problems 3, 4, and 5 on this worksheet, I'm going to ask you to go ahead and create your own description of the Ferris wheel. I'll do one more example of that right now, but you're not allowed to use the numbers that I'm going to use for my example. You're going to have to come up with your own numbers. The first thing you need to focus on to create your own numbers is look at the parameters of the graph. We're going to have the same height, maximum height of 60. Okay, so you want your graph to be able to fit on this grid right here. We're going to have a maximum time of 50, so you're going to have to stay within those parameters. All right, I'm going to go ahead and create my description of my Ferris wheel here so I can show you how I want you to do it on the assignment. What you can do is to fill this out today, and then when the assignment releases on either Wednesday or Thursday, depending on whether you're on an even or odd schedule, you can go ahead and copy from this worksheet straight onto your assignment, and you've already got that part of it done, the first part of your assignment. Okay, but again, you cannot copy what I'm using on my example here. So go ahead and pause the video now, and then turn it back on so you can try it, and turn it back on to check your work and make sure you're doing it right. So pause now. Okay, so here what I've determined is I'm going to have a radius for my Ferris wheel of 10 feet. And I'm going to put the center of the wheel 20 feet above the ground, and I'm going to rotate counterclockwise every 30 seconds. So I've gone ahead and given a quick sketch of what my Ferris wheel is going to look like over here on the right. There's my sketch showing the radius of 10, and then I drew another circle around it just saying, hey, it's going to take 30 seconds to go one full rotation. So what I know based on this information is I know the center of my Ferris wheel is going to be at 20. So that's kind of where my midline is going to be, 20. So I can sketch my midline. I know that my radius is 10, so the maximum it's going to be 10 seconds above that. But before I can do anything with that, I know I'm going to start at 20 feet. 30 seconds later, I'm going to be at 20 feet again. And halfway between 0 and 30, half of a rotation is going to be 15 seconds in. So at 15, I'll be at 20 as well, which means I'll also be at 20 at 45. The next step is to find my maximum and minimum values. My maximum is going to be halfway between 0 and 15, which is going to be 7.5 seconds. And since the center was at 20 and the radius was 10, the maximum value height is going to be 30. So I go to 7.5, 30 for my height. The minimum is going to be 10 less than 20, so that's going to be at a height of 10. And that's going to happen at 22.5 seconds. So it's going to be somewhere over here. And then I'm going to hit the maximum again at 37.5 seconds. That's going to be over here. And then I'm going to hit the minimum one more time, which will be just off my graph on this situation. I can go ahead and sketch it now. And I'm going to draw arrows again to show this graph goes on forever in both directions. The next step, I need to write the equation of the graph I sketched for question 4. So I'm starting with, I know what my A value is. That's going to be my radius, 10. I know my midline is going to be how far above the ground I am. So my D value is going to be 30. The tricky part here is figuring out what my B value is. So what I need to ask myself first is, what's the period of the function? Period in this case is 30 seconds. It makes one full rotation in 30 seconds. One full rotation is 360 degrees. So I need to say 30 equals 360 divided by B. And then I need to solve algebraically again for B. So multiply both sides by B first. The B's are going to divide out on the right side of the equation, so I get 30 times B equals 360. I can divide both sides by 30, and I end up getting B equals 12. So I should have my B value equaling 12. And now I can go ahead and write my equation. My equation is going to be y equals 10. This is a sine function. All of our functions today are sine functions. So 10 times sine, in parentheses, 12t, because our x-axis is being represented by t today, plus our midline of 20. That's how we're going to write this particular equation. Now for problems 6 and 7, we're going to be asked what happens when we affect the radius of the wheel, the height, and the rotation speed of the wheel. So the three things we really want to focus on for part 6 is the graph. Well, that would be the amplitude, the period, and the midline. Okay, so which of these three things are going to affect which? That's kind of what I'm asking you to look at here. So problem 6 says the radius of the wheel. Well, when we talk about radius, that's a direct effect of amplitude. Problem 7, the height of the center of the wheel was greater or smaller. So the height of the center of the wheel, well, that affected the midline. And then the last part, the wheel rotates faster or slower. That was what was affecting the period of the function. Okay. It's problem 7 now, is talking more specifically about the equation. So when we're talking about the equation, we're talking about y equals a times sine of bt plus d. T is our time. All right. The radius of the wheel is larger or smaller. Well, that's affecting the a value, or the amplitude, which we spoke about in problem 6. The height of the center of the wheel is greater or smaller. Well, when the height's greater or smaller, that's the d value, which represents the midline. And then the wheel rotates faster or slower. That's representing the b value, which is related to the period, because the period equals 360 degrees divided by whatever our b value is. The last part, problem 8, is going to ask us to write the equation of the height of a rider on each of the following Ferris wheels, t seconds after the rider passes the farthest right position. So the first one says the radius of the wheel happens to be 30. Okay. The center of the wheel is 45 feet above the ground, and the angular speed of the wheel is 15 degrees per second counterclockwise. Now for our equation, we can say y equals a times sine of b times t plus d. All right, t stands for time, the a value stands for our amplitude, the b value is representing something to do with our period of the function, and the d value represents the midline. Now for this particular problem, the a value is 30. So we can just say 30 times sine of b times t. This one's a little weird. The wording says the speed of the wheel is 15 degrees per second counterclockwise. So it's already telling us it's going 15 degrees every second. That actually happens to be our b value right there. So we don't actually need to use any calculation to find the period. In problem part B, it says it moves one revolution every 15 seconds. That's the difference. if it's already given us 15 degrees, that's just our B value. So we get kind of lucky with that one. The last part here says we're going to be 45 feet above the ground. So we can just say plus 45. There's our midline. All right, the last problem today, problem number 8, is going to tell us the radius of the wheel happens to be 50 feet. The center of the wheel is at ground level. And when we hear ground level, it also says here you spend half your time below the ground. But ground level really just means that the midline is at 0, d equals 0. And then the last part here, the wheel makes one revolution clockwise every 15 seconds. Clockwise is key here because that's telling us we're going the opposite direction. So before, when we were going counterclockwise, that's always a positive direction. Clockwise means negative direction instead of a positive direction. That's the big difference here. So we can start by writing our equation. Y equals, our radius is 50, so that's going to be our amplitude. We're going to go up 50 from the midline, down 50 from the midline when we're sketching this graph. We have our sine value. Our B we're going to need to calculate. We'll come back to that in a second here. And then the last part, our midline, is plus 0. So we could write plus 0, but technically I'm not going to write that. I don't need to. I know anything plus 0 is just going to be that number. So I'm not going to write that part. The other weird part here we need to talk about, it's a negative direction. So we're going to need to make this function negative. We're going to need to put a negative right there to represent the clockwise rotation. Whenever we say clockwise, we need to put that negative in front. It says it's going every 15 seconds. So remember our period, to find that B value, we're going to say the period is 360 divided by B. In this case, the period is 15. So we can go ahead and multiply both sides by B, divide both sides by 15. We're going to end up getting 24 for our B value. So this thing ends up equaling negative 50 sine of 24t. And that's what this last problem will look like. All right, so remember to check in with your teacher for office hours if you have any questions about this stuff. It's kind of a lot this week in terms of this new sine function graphing thing. And also make sure to take a look at that assignment on Wednesday. Like I said, the first part of the assignment is going to be problems 3, 4, and 5. Just don't use the numbers that I used in the example today. Have a great week, guys.